Hi. Well, now for something completely different. Hello, I'm Claire. I'm a musician, an artist, and science journalist based in Los Angeles. I'm so glad to be here. Thank you for the invitation. Today we're going to talk about biology, which I hope will be an interesting side quest for everybody here, and maybe even generative in terms of thinking about algorithms. But we'll start with a little really well-traveled tech history. 1965, an engineer named Gordon Moore made a prediction. You probably know it. With every coming year, the number of components on each integrated circuit would double, making computer chips exponentially smaller, faster, and more powerful until such time as they reach the cold, hard edge of physics. We call this prediction Moore's Law. Moore was the co-founder of Fairchild Semiconductor, which was the first company to apply silicon to integrated circuits. Later, he was the CEO of the chip manufacturer Intel, where my father worked for 30 years, from the late 70s to the early aughts. 30 fairly transformative years for the computing industry, obviously. 30 transformative years for my family. The microprocessor boom brought us to the US and funded my education. When I was a child, my future was forged in the crucible of Moore's Law, in the expectation of a faster, better, cheaper, more powerful tomorrow. Moore's Law is a lot of things. It's a self-fulfilling prophecy, a capitalist projection. It's good PR. It was a convenient benchmark for the technology industry's ambitions, but it's not a law of physics. It's not a law of nature. Their evolution, quote unquote, has inspired much growth, quote unquote. But computer chips aren't living things. Quite the opposite. They're stone, they're mineral, they're silicon, tungsten, cobalt, copper, and tin. They're elements mined from the earth at great cost and animated by electricity, language, capital, labor, and time. But none of us are distracted by that because it's all just rocks in the end. And that's the magic of computers, right? It's also the magic of people, depending on how you look at it. By miniaturizing rocks onto wafer-thin chips, we have made them into oracles. And we've made people like Gordon Moore into priests. We've deputized them with the responsibility of telling us what the future portends. And what a future it has been. I mean, these rocks have come from the deep time of the earth, from the geologic eons, and in a matter of only decades have become powerful enough to model the climate and send sycophantic sentiments spilling from chatbots. And yes, that's a lot of alliteration. It's amazing what we've done with rocks. We should be proud. But there's a limit to what rocks can do. Moore's Law is not set in stone, it's just been pressed upon it. And the cold, hard edge of physics is here now. Moore himself admitted this. Miniaturization can only take us so far. The cost of manufacturing next-generation chips grows more and more prohibitive the closer we get to the physical limits of miniaturization. The smaller the chips get, the more expensive it is to make them. Unfortunately, there's only so many rocks left, because demand for the high purity, high quality silica sand that's used to make silicon chips is so high that we're currently facing a global irreversible shortage of sand. And we all know that the supply chain for minerals commonly used in computers, smartphones, and batteries fuels bloody conflict, exploitation, political instability, and chaos around the world. So the question I come with you today is, what comes next? After we've drawn blood from the final stone, if we are to predict our own future, make our own laws, what might we want it to be? Personally, I'm interested in transcending smart rocks, in transcending miniaturization once and for all, and rather than silicon, tungsten, or tin, mining our future from far stranger stuff. In fact, I'd like us to stop mining completely and start growing. And if that sounds impossible, then you've never encountered the slime mold. Did I just hear someone say yes? Cool. Well, that's easy enough to correct if you haven't, because unlike silica sand, slime molds are abundant on Earth. All you have to do is go to your nearest forest, the damper the better, and look under a log. Look in the loam and the rot, in the decay. That's where you'll find them. And when you do, you'll probably think you're looking at a mushroom. And you wouldn't be the first to make that assumption. Slime molds are so unusual that they've been mischaracterized and misunderstood throughout history. Their Latin name is mycetozoa. Myceto as in fungus, zoa as in animal, fungal animal. But they're neither. They're not fungi, they're not animals, they're something much stranger. This is Physarum polycephalum, the most charismatic and probably famous of the slime molds at this point. It spends most of its life as a free-floating, invisible amoeba, but when times are scarce and resources are scarce, Physarum amoeba come together into what's called the plasmodial form, a collective acellular organism. It's visible to the naked eye as this unctuous, electric yellow, enveloping slime. And within that slime, the loose nuclei of the amoeba stream back and forth in a rhythmic shuttle flow. You can see it here slightly sped up. Propelled by that pulsing movement, the plasmodial Physarum travels through its environment, actually quite quickly for a creature of this size, at about 1 millimeter per second. And as you can see, as it does this, it forms and deforms its body as it goes, sending out these searching tentacles called pseudopods as it forages for food. Where it finds no food, it retreats, leaving behind a chemical trace known as an extracellular slime. That trace signals to the plasmodial body not to return. There's no food here, don't come back. The extracellular slime, the trace, and the capacity to reread that trace constitutes a kind of spatial memory in an organism which has no mind, has no central nervous system, has no awareness that it's doing so, and yet somehow still Physarum can explore and map its world in staggering detail. And that means that this humble organism, in the right context, can solve mazes, can easily find the most efficient path between points on a map, can design resilient networks. It makes quick work of the U-shaped trap problem used to test autonomous cars and robots. Physarum, in a range of experiments, has modeled the roadways of ancient Rome, traced a perfect copy of Japan's interconnected rail networks, charted new paths across Mars and the Moon. It's especially expert at the kinds of network optimization problems called traveling salesman problems, which are extremely difficult and, more importantly, extremely inefficient to solve with conventional computation. As you no doubt know, central processing units can only tackle one operation at a time, no matter how fast a CPU is. Evaluating thousands, millions of potential routes, one after the other is time-consuming work, and it grows exponentially more difficult with every additional stop. Because it requires so much computing muscle, the TSP is often used as a benchmark to test the limits of new processors, and many scientists believe that an efficient algorithm for solving it simply doesn't exist. So, what are we to make of the fact that a slime mold can do it? Well, what the slime mold does is not linear. You can think of it as morphological computing. It's thinking with form. And that might be counterintuitive to us, but Physarum thinks with its body rather than with any kind of brain. What does that mean, to think with a body rather than a brain? I think an interesting way to think about this question is to look at the inverse, which is a brain without a body. And that's a fair enough description of the ambitions of deep learning, the project of emulating the synaptic connections of the human brain through artificial neural networks. AI, historically, emerges from disembodied models of the human brain, because the assumption has been that that's where the intelligence is, right? Well, it certainly is where some of the intelligence is, but if you actually look at biology, you'll find that intelligence is a lot more amorphous than that. Physarum, for example, shows us that there are ways of thinking that are purely embodied, which transcend brains entirely, and which happen to be quite good for certain kinds of problems. So when we consider the mammalian brain, or the human brain, in isolation as our model for intelligence, we ignore that. We ignore those avenues and those solutions. We also ignore the fact that even in humans, the brain is situated in a body. And in that body, microorganisms outnumber cells 10 to 1. So we're not thinking about what those organisms are doing, what they might know, how their intelligence, however rudimentary, might influence our actions. If you know anything about the gut-brain axis, that's quite a bit. We're also ignoring what cognitive processes might be at play outside of our brains, in our bodies, in our non-neural cells, in the cells that make up our bodies. Can those remember? Do they have their own ways of solving problems, of adapting to change? These are open questions in biology, but what we're beginning to learn is startling. Because for decades, the prevailing wisdom in neuroscience has been that memory and learning, these foundational aspects of intelligence, are consequences of synaptic plasticity in the brain. So the connections between clusters of neurons that are simultaneously active during an experience strengthen into networks that remain active even after that experience has passed. This idea is decades old. It's commonly expressed by the adage that neurons that fire together wire together. It's fundamental to our understanding of memory, and for most neuroscientists, it constitutes the definition of memory. It also undergirds the design of all artificial networks. But again, more and more biological research suggests that synaptic plasticity, although important, is not the whole story, because memory and learning and the behaviors that they empower take many, many forms in the natural world. Look at bacteria, for example. The most ancient and arguably most successful life forms on Earth. All bacteria perform chemotaxis, which is the process of moving along chemical gradients towards more favorable environments, so towards greater densities of sugar, away from toxins and poisons. They wouldn't be able to do that without the capacity to continuously compare past and present conditions. Chemotaxis, by definition, is a process of continual assessment and reassessment. To know where they're going, they have to know where they've been. Now, this is an aneural process. I won't get into the details of E. coli chemotaxis, but suffices to say that there are no synapses involved. It's a matter of chemicals activating proteins that change motility. It's not what a neuroscientist would call memory. But like the morphological computing of the slime mold, it functions as memory. And if we expand our definition of memory to encompass what it does, rather than just what it is or how we've named it, we will find it is everywhere. Okay. Bacteria are prokaryotes. We're eukaryotes, as are most living things on Earth. So is this. This is the ciliate, Stentor roselli. It's a pond-dwelling unicellular creature. Its basic physiology is that it adheres to a rock or a solid surface in a body of water using this sticky little foot called a holdfast. It extends this trumpet-shaped opening and uses the movement of its cilia to sweep food particles into the opening. It's a physiology that might look kind of plant-like to you or even animal-like, but Stentor is just one cell. It's a single cell, no nervous system, no brain, just a cell. Now, if you irritate it using, for example, a little pipette filled with dye or microparticles like this, it will react. First, it will turn away from the source of the irritant, like any living thing, perhaps. Then, if that doesn't suffice, it will reverse the direction of its ciliates. So instead of sucking water in, it will spit water out. If that doesn't work, it will contract sharply into its little holdfast foot. It'll poke its head out again to see if the coast is clear. If things haven't changed, it'll contract again, over and over again, until finally, when it's well and truly exasperated, it will detach from its base and swim away. Now, that's a hierarchy of behaviors. Each of these behaviors requires prior knowledge of the previous experience, right? You can't ratchet up your response to an irritant if you don't know what came before. We don't know by what mechanism this occurs. Clearly, it's an intracellular phenomenon, some molecular mechanism, but it is undeniably also a form of memory. It represents an awareness, and I realize that's a loaded term, but some awareness of past and present environmental conditions. And that awareness is present in many, maybe possibly all non-neural cells, which means single cells in the body as well. So not just unicellular creatures, which are evolutionary ancestors, but single cells in a multicellular body like ourselves. There was an amazing study last year out of NYU that found that human kidney cells can remember. And not only that, they exhibit what's considered to be a cornerstone in human memory and learning, a phenomenon called the spacing effect. Like us, they remember things longer if they're exposed to new information at spaced intervals rather than crammed in all at once. So it's kind of like cramming for a test, you know. If you stay up all night cramming for a test, you tend to forget everything within a couple days. But if you study consistently every night, you'll remember longer. That's true for people at an organism level. It's also true across the living world. We found that it's true in bees, fruit flies, and sea slugs. They all exhibit the spacing effect. All mammals exhibit the spacing effect. But now we know that it also permeates us down to the cell, suggesting that there are these far more basal forms of knowing, of cognition, than neuroscience has previously acknowledged. The implication is that cognition in some form is everywhere. It's naturalized down to the cell. And we're just now beginning to uncover this. There's still so much that we don't know. And even the things that we do know, we struggle to represent using conventional computation. So going back to our rocks versus slimes problem, It's really difficult to model the complexity of natural systems using rock-based computers. It just is. This, for example, is, well, a rendering of the microscopic roundworm C. elegans. It's one of the most studied organisms in all of biology. It's been a model organism in biology since the 50s. It's a tiny worm about as long as a hair is wide. And we know basically everything you could possibly know about it. We have mapped its genome. We know where every single cell in its body is and how it was formed. We have an electron microscope map of all 302 neurons in its brain, and we can turn each individual one off and on using genetic imaging technologies and see how that influences all the other neurons. We have a complete wiring diagram of this organism. And it only has 302 neurons in its brain. We have 86 billion. So you would think that's about as simple as a brain can be, and that something like artificial worm intelligence might be achievable in our lifetimes. Something simple. It's not. The dynamic behavior of those 302 neurons is incomputable. Simulating it is one of the thorniest, most interactable problems in computational biology. People have been trying to do it since the 70s. One researcher I talked to about it once told me that the idea of C. elegans simulation is like a cathedral to him, that he didn't expect to see it done in his lifetime. Even if all of the resources and all of the energy and all of the funding in all of biology were directed towards this problem, it would still take decades. It would take enormous amounts of data from living worms. It would take enormous amounts of compute just to do something that a worm does with nothing, right? With compost and sunlight. And I mention this merely just to underline how inadequate our existing computational paradigms are to express the complexity of nature and to humble us a little. That is not to say it's not worth doing. It is. It's a good thing to know the limitations of what our technology can express. And even incremental progress in this field is generative. Worm AI, if we can ever achieve it, might someday be a stepping stone to fruit fly AI, and then sea slug AI, and rat AI, and maybe someday even true human AI. We have to start somewhere. Lessons from the worm, lessons from the slime mold, they can help us understand how cognition works in non-neural systems. And even with a fragment of understanding, a slice of understanding, we can do amazing things. Physarum, for example, is already helping us optimize and build more resilient networks. Mathematicians have even simulated the tiny Physarum to map the largest scale structure in the universe, the cosmic web. This is an example of looking around us at nature to find useful solutions to problems in the human world, because we might think that our problems are new and modern and unique, but they aren't. Our problems are problems of survival and resilience and resource management, and that is not new. One of my favorite scientists is an ant scientist at Stanford, Dr. Deborah Gordon, and she found a few years ago that the algorithm harvester ants use to regulate their foraging behavior across the Arizona desert, to determine when to send out foraging ants to get resources and when not to, is functionally identical to TCP/IP, the transmission control protocol used to regulate packets of data traffic across the internet. Now, does that mean that ants are computer scientists, that they're somehow brilliant? No, they've just had millions of years to solve a problem that we've only had for a few decades. It begs the question, what other problems might we share? What other solutions can we borrow from nature? Because ants and slime molds and worms, they're interesting model organisms in a laboratory context, but they're in no way unique. The computer scientist Salim Aql observes that computation is ubiquitous in the universe. To be is to compute. And that's not really a metaphor. In fact, it's increasingly common to hear biologists talking about algorithms, using terms like information processing, to talk about what life is doing. Because at the most fundamental level, what is computing? It's the capacity to process input, let's say information from the environment in the context of an organism, to store or encode that information in memory, which conveniently is the same term for biological and computational systems, and then to change behavior or output based on that encoded information to optimize performance or survival. And then ideally, to feed the output back into the system and continuously improve it. That's basic to computing. It's also basic to the survival of any living thing. What we think of as computing, operations in silicon and tungsten and tin, is a specialized instance of a process that is much broader and more ancient. And we need to start thinking about it and including it in our consideration of what computing is and means, because the more we broaden our definition To include this, the more solutions we have at our disposal. Computing is a process that spans material substrates, phyla, millennia. It exists at many scales and many degrees of complexity. Again, to be is to compute. To compute is to be. And that is the inverse of how we think about computation now. Since the invention of giant calculators, data processing machines in the mid-20th century, we have bent over backwards to make our world legible to them. Hat tip to the great James Bridle for this observation. When we feed structured data into computer systems, we compartmentalize the complexity of reality to fit a mathematical, logical model of the world, which has worked for many, many things, obviously. But in that process, we have also subtly and continuously degraded and diminished life. Life is messy. It doesn't reduce well because it is by definition dynamic. Living systems can't be reduced down to their component parts. I mean, they can, of course, but that doesn't explain what is going on with them. Living systems and the behavior of living systems emerge from the interaction of parts at multiple scales simultaneously. It is, as complexity theorists like to say, an emergent process. And there's so much noise today about AI tools and agents, about fellow travelers that will help guide us through the coming decades or hasten the demise of art, labor, and our livelihoods. But we already have fellow travelers all around us and, more importantly, within us. And if nothing else, they remind us of the need to be mindful of the difference between representation and reality. Because the way that AI models understand the world and feed it back to us is purely semantic. It's divorced from lived experience. AI systems are trained on words, symbols, code, sounds, images, all second-order representations of reality. But intelligent living systems are primarily engaged in an embodied first-order relation with the world. Physarum slime mold has no sensory organs with which it can represent the world to itself. It simply negotiates with its environment physically. It maps the world through being, in a give and take that is chemical, tactile, bound up with the consumption and excretion of matter, the transformation of matter through digestion and decay. There are no intermediaries, and that is extraordinarily efficient. It's also extraordinarily relational. The slime needs its environment to compute. It needs a context. The environment, which includes not only the material world, but all the actions taken on it by other living organisms in the past, dictates the form of the computation. And that's true for all intelligence on Earth. All information processing on Earth emerged as the result of a very, very long, very, very open-ended relationship with the world, conversation with the world. And that's a process through which every living thing found a mind, an appropriate mind for its context, in conversation with other minds. Fun fact, neurons first evolved around the same time that animals started to eat each other. That is to say, the fact that we have more complex thought at all emerges from an evolutionary necessity to be aware of the presence of other animals. Thought does not occur in a vacuum. Now, that doesn't mean that intelligence has its origins in hostility. I don't want you to read it that way, because in many cases, avoiding predation is a question of collaboration. But it's evolution, time and time again, that has given us memory, the capacity to learn and adapt the fundamentals of intelligence. So why not work towards intelligence systems from the bottom up rather than from the top down? It's the only way we know that it's actually worked. The fact that I'm here speaking and you're here listening is testament to that. What does that actually look like? Well, I'm going to give you a couple of more concrete examples. One wetware, one software, although it's ambiguous, and you can tell me later which one you think is more alive. First example, xenobots. Is anyone familiar with xenobots in this room? Cool. Our Tyler last night was talking about xenoharmonics. This is different. Xeno in this context is Xenobus laevis, which is a voracious clawed frog native to the wetlands of sub-Saharan Africa, a long-standing model organism in biology. Bot, of course, robot. Now what happens when you put those two things together? You get frog robots, living robots. Here's how you make one. You start on a computer with an evolutionary algorithm. You tell that algorithm what you're working with, which in this case is embryonic frog cells, and you tell it what you want it to make. new organisms with certain capacities and motility. The algorithm then generates random solutions to that problem, setting hundreds of these oddball shapes loose in virtual petri dishes and seeing which one survives. Then you make a leap from simulation to reality, from software to wetware. You start with undifferentiated Xenopus laevis stem cells. You literally take them from a frog's embryo. And you pipette them carefully into a little mold. And what happens is the cells will naturally cohere together, forming this tight little sesame seed-sized sphere of living matter. Then a microsurgeon, using a tiny scalpel and a teeny tiny cauterizing iron, will physically carve those spheres into shapes that were suggested by the evolutionary algorithm, which gives us computer-designed creatures brought to life. Xenobots are the first living creatures whose immediate evolution occurred inside of a computer and not in the biosphere. What's interesting about them, there's so much that's interesting about them, but one thing is that they behave exactly like the silicon counterparts. So they move and swirl around in the real-life petri dish just like the virtual ones did in the simulated petri dish. And like slime molds and ciliates, they don't have brains. They're just a cluster of cells. They're kept alive in this nutrient goo, which anecdotally biologists call the nutrient goo that they feed these guys with media. So cells are cultured in media, just like us. But despite that, they have a form of agency, kind of nano-agency, maybe. The researchers who build these don't fully understand their behavior. Sometimes the xenobot, you can kind of see it in this, will kind of head off in one direction and then abruptly turn around, as though it just changed its mind. Sometimes, as you see here, they'll swirl around, herding loose cells into yet more xenobots, which is a process the team behind this calls kinematic self-replication, which is a kind of wordy way of trying to say reproduction without actually saying it. The frog cells are just the beginning here. The xenobots were first made about 4 or 5 years ago. Now it's possible to create anthrobots from human cells, and to seed these biological robots with neural precursor cells so that the resulting organism forms a rudimentary nervous system that is totally without evolutionary precedent in the world. Now, what researchers are doing here with this is seeing what happens when you put cells into novel configurations and novel contexts, and in doing so, they are discovering the fundamental competencies of living matter. What xenobots, anthrobots, and other biobots demonstrate is that cells are adaptive and can be autonomous. So even in the total absence of a body, they can still get together and solve problems. They can move through mazes, they can collaborate, they're competent agents, able to assemble themselves into larger structures and pursue goals. And this squares with what we were saying earlier about memory and cognition reaching down to the cellular level. So the bad news here is that there's nothing magical about our brains. Neurons just perfected what regular cells were doing for millennia. The good news is there's something magical in everything else that's alive. That cognition is everywhere in different degrees and combinations, and I think that's much more exciting. But the untethering of cognition from the neural architectures of the brain opens up a lot of new avenues for thinking about how we go about creating intelligence in computers. For one, it raises the question, what kind of intelligence systems could we build if we were not trying to reproduce brains, but rather something more like frog cells or human cells? It also invites the question, what kind of intelligence systems could we build if instead of using a rock-based substrate, we actually used these living materials, which are fundamentally very competent? Conveniently, both cells and conventional computing components respond to electrical signals, right? Which makes them surprisingly easy to interlink. It's possible, for example, to grow cultures of human neurons directly onto microelectrode arrays in the lab and use those electrodes to both stimulate the neurons and record their output. Now, this enables a very basic form of programming and a potential avenue for training living systems to perform simple tasks like image classification, perhaps, or even playing games. Oh, blank slide, cool. You may have seen a viral news story a couple weeks ago about human neural cultures playing Doom. Did anybody see that? It was making the rounds. That's from a company out of Melbourne, Australia called Cortical Labs, who have done just what I'm describing here. They grow two-dimensional neural cultures directly onto microelectrode arrays and have figured out how to stimulate them in such a way that the neurons optimize themselves for learning tasks. They took a very well-known theory in neuroscience and adapted it to this application. Basically, they've found that the neurons respond really well to structured stimulus. They like regularity, and they will adapt themselves to any situation where the stimulus they receive is regular. So if you give them nice regular pulses of electricity after they complete a task, they will learn that task quickly. If you give them chaotic bursts of electricity, they won't. Anyway, they figured out how to do this. And now these neurons can play Doom. Only 3 years ago, these same neural cultures were playing Pong. So that should give you a sense of how quickly this tech is evolving. Cortical Labs is a really interesting company. They've also built the first purpose-built biocomputer, a machine called the CL1, which can keep a human neural culture alive for 6 months, and which researchers can use to directly experiment with their own techniques for programming living matter. And for those who don't want to worry about actually keeping their computers alive, because it's a big ask, they also run a cloud service of 120 networked CL1 computers that are directly addressable in Python. So the biocomputing future is here. It's not speculative, it's actually happening. It's just early days, like really, really early days. I should probably mention that the neural cultures playing Pong and Doom do so very, very badly. They suck at it. They can do it, but they suck at it. These neural cultures are like any living matter. There's a lot of challenges. They have their own goals, which might not be compatible with ours. They're delicate, prone to infection. There are plenty of engineering challenges involved in keeping them warm and well-fed and alive. They're mortal. But I would also like to remind you that this is what an integrated circuit looked like in 1961. And only 4 years later is when Gordon Moore felt empowered to both predict the exponential growth of the circuit and with Moore's law, and create the conditions for that growth to occur. The history of technology has been driven, for better or for worse, by these kinds of grand ambitions and proclamations, so I don't think it would hurt us to have a little vision here. Because life has been computing for a millennia, and now we're catching up. And fortunately, we can piggyback on all the things life is already good at: adapting, learning, solving problems. I interviewed the chief science officer of Cortical Labs, Brett Kagan, and he said to me, "Why emulate what you can harness?" That's a strong logic for biocomputing, I think. He also said sufficiently advanced technology becomes indistinguishable from biology, which I'm going to steal. Our understanding of the living world has always evolved alongside our technology. For the first half of the 20th century, biology was dominated by a mechanistic, linear, reductionist worldview. There was this idea that the structure of things determined their function, and that cells were just automata in more complex systems. It was believed that every living thing could be taxonomized and dissected and broken down into its parts and examined under a microscope. Biologists felt that by breaking life down, it could be understood like a machine. And that reflected the computational paradigm of its time. That we understand life to be a dynamic process now, one defined by what emerges from the interactions in time of all those constituent parts, is partially a consequence of our changing capacity to model it with computers. Simply put, our computers are powerful enough now to help us think differently about life. They can help us see patterns that were previously invisible to us at multiple scales. And I'd like to think that now it's life's turn to help us think differently about computers. I'd like to end by expressing to you my hope for the future, which is also kind of a call to the deep past. The gap between technology and life gets bigger the more we examine it, like all interesting things. But I do think that by bridging it, or at least trying to, we can save ourselves from our worst impulses. And I don't just mean that I someday hope on some solar punk ecological level that we'll someday have machines that are, like I said at the beginning of this talk, not mined but grown. I mean that we might also be able to use those machines to understand the living world more thoroughly, to understand the patterns underlying its creativity and resourcefulness, its mutualism, its remarkable capacity to adapt, its relentless drive to survive, to adapt, to thrive. I hope that we might find a way to understand the world using tools modeled after the world, tools that are generative, resilient, even alive. Tools that could die. That's interesting, isn't it? Tools that are not static and unforgiving or as unyielding as stone. Because I think then we could finally become what we're meant to be, which is just a way for the world to know itself. Thank you. Okay. I think we have time for questions.
My goodness, Claire, that was mind-blowing. Really, really amazing. Yes, we have time for questions. Anyone have questions for Claire?
We can also talk afterwards if you're shy. Yes, in the green.
The green, yeah.
I caught like kind of the latter half of the presentation.
Cool.
And personally, I'd say I'm a bit of a Luddite.
Nothing wrong with that.
I thought it was just so... I guess my question is, understanding the world better is something that naturally I think we as humans want to do because we're very curious and tactile and all that. But we're talking about living machines, which we are, and which you went into deep detail on. And I guess it's just this weird kind of thought loop I'm having where we are the living machines, everything around us that's alive is a living machine. So what would living machines in your context look like, and what do you think that these living computers would actually help us learn, I guess?
Great question.
yeah.
I think we have this idea of what computing is it's predicated on the computers we have. So when we say living machines, your mind automatically goes to like a MacBook with like goo coming out of it, you know? Like that's our model. But I think if we, again, expand our definitions, we can think about computing really differently. A lot of these early biocomputing projects, like some of the first and most interesting applications are just for like sensing, for creating embedded biodegradable living sensors that help us, you know, measure atmospheric and climate change in a more sustainable way, allow us to understand what's happening in soil networks, allow us to understand what's happening in the health of various ecologies. We can kind of deputize living machines to report to us about what's happening in the natural world as kind of intermediaries. I think that's a pretty beautiful vision. But I also imagine that these things will, surprise us. Who knows? I think once we start computing, for example, with human neurons, if we can get past the ethical complexity of that and have a real measured conversation about it as a society, it's just going to be a completely different paradigm. We'll have new problems to solve by then, I imagine, but we might have new solutions as well. So I don't know. It's such an open question. Yeah.
Amazing.
Okay.
Anyone else?
Yeah.
Yes. Cool.
T-shirt. Sorry.
So at the end there, you kind of ended it with the distinction between like computing with rocks versus the slime mold. That just made me think of something I read, something about finding, people were finding these like veins of minerals in the earth and measuring that they had some kind of electrical signals going between the networks of minerals.
Oh.
So I didn't know if you had heard anything about that. And I was like, maybe there's even a crossover between like the two ends of the scale there.
Oh, that's really interesting. I haven't heard anything about that.
Yeah, I'm not sure. It could have been totally fake too.
It's honestly impossible to know these days. But, I'm not saying that, like, rocks are fundamentally, like, amoral or something. Like, I think actually, like, there's a lot of interesting things happening on, like, a nanoscale in materials. There's all kinds of weird porosity and like, there's a really amazing book by this nanotechnologist named Laura Tripaldi called Parallel Minds, which I think if you're interested in this, you would really like. It's all about sort of the fundamental intelligence of all materials. because there are people doing like computing with liquids and in microfluidics, there's ways of like exploiting the physical affordances of what's going on in materials at a small scale to do basic forms of computing as well. So it's really about intent, I suppose. But in this book, she writes a lot about how nanotechnologists don't think of like boundaries between things, that at the scale of like, with the scale that they're looking, like everything is an interface, and that at a cellular level, like everything is mixing and commingling, and there are like interesting chemical and material reactions happening, and that those can be exploited for all kinds of interesting computational applications. So yeah, I mean, it's a broader thing, but I would love to read about that. Yeah, yell.
Yeah, so I was just curious what you think of computing, like moving forward. Like previously, the systems were kind of stuck in like a determinism, where we kind of know exactly what the output is going to be, and as we move forward, we're moving towards like more stochastic processes. Like even AI has like the concept of like.
Yeah.
And as we integrate more like biological like principles within that, we do have more stochastic processes. And I'm curious, what do you think that, like, what sort of implications you think that has to computation moving forward? If, like, does that mean that we can expect like everything to come out of it, or does that just show that we have like currently a lack of understanding of what those?
I think it will give us a more accurate picture of the world, don't you? I mean, if that's what we're trying to understand, then I think, like I said at the end, it's like using tools that are modeled after the world to understand the world, we'll have a better understanding of what's really going on. We won't be like creating these, we won't be compartmentalizing anymore. We'll be sort of in a more genuine conversation with the world. I mean, it's philosophical, I suppose, and I don't really know what that looks like in practice, but that feels exciting to me. Yeah. Oh, cool shirt. Oh wait, sorry. Him first.
Sorry. Do you think that the plates of human neural cultures have an inner experience of the world?
This is a really interesting. I'm working on a feature right now for Wired about this, like, because I skipped over the cortical labs work. It's two-dimensional neural cultures. You can also make three-dimensional neural cultures called organoids, which you take undifferentiated stem cells from an adult donor. You induce them into becoming embryonic cells, and then you induce them into becoming neurons, and then you put them, kind of like the xenobots I was showing you, they cohere into these little orbs, and you can like do really interesting things with those. And all the neuroscientists are like, please don't call them mini brains. They're not brains. But then like 5 minutes later, they're like, anyway, this mini brain, like, anyway. But nobody who is working in biology labs and cellular culture is comfortable with the consciousness conversation. Nobody wants to say exactly how consciousness emerges or whether or not these cultures they're working with have anything like agency, experience, a sense of self in the world. There's a couple factors working against consciousness in these kinds of cultures. One is that there's very little information passing between the culture and the world. I mean, historically, this has been the case. When you're experimenting with cellular cultures, they're in the petri dish and that's it. They don't have sensory organs. They're just kind of in an island. Now that we're doing this kind of electrical stimulation, that question has really changed, and it appears like at least the argument that they're isolated from sensory reality isn't relevant because we are giving them a version of experience. And in fact, the first paper that Cortical Labs published about the Pong work was really like widely contested in the neuroscientific community because they used terms like sentient. And they said that, these cells are embodied in the game world. And, there's lots of argument about semantics, and it's a very cross-disciplinary field, so there's a lot of miscommunication and people talking at cross purposes. But I mean, there is a threshold somewhere between 1 million cells and 86 billion cells where consciousness emerges, and we don't know where that threshold is. We don't know if it's a line or a gradient. We don't know if it's something that occurs at a specific number or if it's more of an emergent process. I think one argument is that we can maybe begin to answer those questions by working with these simple models of cognition, right? How you feel about that ethically, I don't know, but it is, for now at least, though, these systems are much too simple to have anything like experience, as far as any scientist is willing to say. But, there's not many guardrails, which is also kind of crazy. Like, there's no regulation or governance around this at all. I mean, there's basic regulation around stem cell research, but questions about what should we do if this thing becomes sentient, or how we measure that. It's really up to each individual lab and their like embedded ethics teams who are often, on the same payroll. So I don't know, brave new world, I guess. Okay, I promised next t-shirt over here that he'd go next. Oh, sorry.
Who was it?
Thanks. You mentioned biodegradable sensors, and I'm wondering, from a material standpoint, what you think about these replacing plastics.
I mean, wouldn't that be great? What do you mean? Who's pro-plastic in this day and age? I actually just saw a paper a couple days ago about people who were experimenting with biodegradable chips using printing with zinc directly onto I don't know, maybe it was bioplastics, but it's possible. We're getting closer and closer to the possibility. But then it's it goes against the technology industry's fantasies of permanence and power, computing has been defined by its material presence for decades. Every time they create a new computer, you have to pretend like nothing ever came before and nothing will ever come after, that this thing is eternal. And it is in a really, truly material sense. But I think how exciting, if we're gonna be buying a new computer every 3 years anyway, why not just compost the last one? It would be great. Anyway. Okay, yeah, you.
Thanks. So you started with the Moore law. Is there anything like the Moore law for the biological computation?
There isn't yet, but wouldn't that make a great hook for a book or an article? I've asked that question to a lot of people in the space, and not yet. I don't know what it would be exactly, but I think we could probably make one up. I mean, that's kind of the claim I'm trying to say, is that Moore's law was just a guy saying this is how fast I want this industry to grow, and then everyone just hooked their hopes on that because there was a lot of money involved. We can make similar claims. It's not like Gordon Moore really knew the future. We can make similar claims if we want to. And then if everyone else can believe them, then we might have a better few decades ahead of us. I don't know.
Thanks.
Yeah. Okay, we can talk about this more later.
Amazing. Well, thanks so much, Claire.
Thank you.
We're going to take a 30-minute break before Nathan Ho this afternoon. So please check out the gallery at the back here as well. We have zines and t-shirts. Check out the zine that's made for the festival here itself. So lots of contributions from many of the people performing, speaking here as well. A lot of great stuff. Thank you, Ian.